So, welcome back to particle physics and the Standard Model. This is lecture 17 and now we are dipping our toes into constructing the Standard Model, right. So, last time we saw a little overview of where we are going with the Standard Model. The first thing we need to do is to understand what we even mean by quantum field theories. So, how do we even put together the concepts of relativity and quantum mechanics that makes sense, okay. So, let me begin with some historic notes on how this was done, alright. Now, from here on I am going to follow Srednicki's book on quantum field theory, okay, if you want to follow along, and in particular I will be using chapters 1 and 3. Okay, chapter 2 is on Lorentz invariance, which I am assuming that you know about already. It is a prerequisite for this course, correct. Okay. So, let us attempt to construct a theory of relativistic quantum mechanics, right, that is what we are getting at here, correct. So, let us begin with an equation that you all know, the one equation that you should know about quantum mechanics, the Schrödinger equation, which tells you how a quantum state evolves with time, right, as determined by the Hamiltonian, correct. So, now if I take a free particle which has no spin, I can now rewrite this with the Hamiltonian operator, correct. So, that is nothing but p square over 2m, and then if I plug in the operator for p, I get minus h bar squared over 2m del squared psi, correct. Okay. Now, of course, I can now hit the state with the position operator on the bra side. I can hit the kit with the position bra operator, and I can now of course rewrite this as an equation on the wave function itself, agreed. So, let me do that because it becomes illustrative later on, and the wave function is just as psi. Alright, very good. Good. So, this is the non-relativistic version, correct. All the quantum mechanics we have learned is non-relativistic, correct. So, that is the reason why I use this operator, which is a p square over 2m. So, what would I do if I wanted a relativistic equation for quantum mechanics? What is the first thing I would try to do? Instead of using p square over 2m as the Hamiltonian, I would try to use basically p square c square plus m square c power 4, correct, under a square root. I will try to use this as a Hamiltonian, agreed, where p is still an operator, right, because I want the Hamiltonian to be an operator, correct. So, of course, it should be clear if I do an expansion what this means. If I take a small momentum limit, then I am going to get an mc squared plus a p squared over 2m plus higher order terms, correct. This is what I would expect just to build intuition. The first term is the energy from just the mass, the second term is the kinetic energy, and so on, right. So, let us see what happens if I plug this in as the operator. It already looks weird to you, right, there is some operator under a square root, but let us see what the physical consequences are. I'm just going to plug that into the Schrodinger equation, and that is going to give me I h bar partial derivative with time, that is going to give this very weird operator on the right hand side, h squared c squared del squared plus m squared c to power 4 under a square root. Good. Now think about this. Can this be a good equation to describe a wave function in relativistic in special relativity? Is this a good way to combine quantum mechanics and special relativity? And do not just say that there is a square root of some operator on the right hand side. Can you think of a physical reason why this cannot be a good equation? It is not just that the right hand side operator is under a square root. What that also implies is that it puts time and space, right, let me call it R, on a different footing, right, whereas we know that you can mix up time and space in a very nice linear way in relativity. That is just what relativity does, right, it puts time and space on the same footing, so that you can write Lorentz boosts, Lorentz transformations in this form and so on, correct, but we have manifestly lost that. So that is already one problem, right. Another even deeper problem would be if you now started expanding the square root, right, in powers of the del square, then you would end up, what would happen then? So we just wrote down the expansion here without a del square, but what are the higher order terms here? I would basically have terms that are order p power 4 and so on, correct. Similarly, over here I will have not only a del square, but basically order del power 4, del power 6 and so on, correct, in the expansion. Now what does that mean? It seems like I seem to have an infinite number of derivatives, spatial derivatives on the right hand side, and that is not a good thing, right. If I have infinite spatial derivatives, it means I am sampling, I am kind of sampling all over space, correct. Put differently, this would make it manifestly a non-local theory, and that is not a good thing, correct. We want locality as well. When we want a relativistic theory, we better make sure the theory is at least local, so that we do not run into crazy things, we do not violate causality and things like that, right. So this alternative is not a good way to do it. So what can we do? We notice that there is still one power of the time on the left hand side, and in some sense there is still one power of space on the right hand side, because the space derivative is under a square root, right, the square of the space derivative is under a square root. So this seems to suggest that it is possible, at least from dimensional analysis, to put them both on the same footing if we just squared both sides, correct, not just square the wave function also, just square the operator. So let us see what happens if we do that. In that case, do you agree that this is what I would get? On the left hand side I have this, and on the right hand side I have, so I am going to actually switch sign. This is how, so Srednicki writes with a minus sign because he uses a different metric, but I am going to use the metric where time has a positive sign and the 3 spatial dimensions, those axes have a negative sign. So, I am going to switch signs here and there, okay, but do not be thrown off by it, it is just a question of metric, it is a question of taste, right. So, I am going to switch Sredniki's sign and I am writing a plus c squared. So, let me erase the metric. Del squared plus m squared c power 4 also acting on this field. Agreed? Now, would you agree that both space and time are on the same footing? They are, right. So, there are 2 powers of time on the left hand side, 2 powers of space on the right hand side, right. So, this is a good candidate, and in fact you have already seen this equation, right. This is indeed the Klein-Gordon equation, and since we did not mention spin here at all, if this state describes a state, sorry, if this describes a particle state, it had better be a spin 0 state, correct. So, the Klein-Gordon equation we know does describe a scalar wave, agreed, okay. But this does not just tell us that the entire equation is actually Lorentz invariant. So, we seem to have put space and time on the same footing, looks like the Klein-Gordon equation, but we should really make sure that this, if this is the equation of motion for the state, that it actually is Lorentz invariant, okay. In other words, if in one frame the coordinates are x mu and in another frame the coordinates are in Sredniki's notation x bar mu, right, then somebody measuring in the first set of coordinates, somebody measuring the wave function or the field in the first set, if they get psi of x, somebody measuring in the second set would get a psi bar of x bar, agreed. So, what is the condition for Lorentz invariance? The condition is these two should be the same. At the least they both should measure the same field, the same state, agreed. The laws of physics should not change across inertial frames. Not only that, one should also demand that the entire equation of motion, right, whatever it is, the Klein-Gordon or whatever, the equation of motion should also be Lorentz invariant. Okay. So, what do we mean by that? So, let us write the equation of motion in 2 different frames. So, this is a Klein-Gordon equation, right. So, I am going to shorten this into, I am going to put the space and time derivatives together into a single derivative that I am going to call dou, okay. It is actually a dou mu. This also is a 4 vector, except this is on space and time derivatives, correct. So, how do I write this? Now, there are 2 derivatives, right. So, do you agree that this is how I would write it? Contracting 2 Lorentz indices, an upper index and a lower index, a contravariant vector and a covariant vector, right. So, let me write it this way. So, it is this plus m squared c squared. Now, I am going to put the h bar downstairs, okay, and this acting on psi of x is 0. So, I have basically just rewritten the Klein-Gordon equation in a compact form. In fact, I can write it in even more compact form. I am just going to call this combination of derivatives, I am just going to call that del squared, alright. So, when you see this, you just have to remember it is actually a contraction of a covariant and a contravariant derivative, alright. So, I just write del squared plus m squared c squared over h bar squared acting on psi of x equals 0. Okay. So, this is in one frame, this is in the x mu frame. How would I write the equation of motion in the x bar frame? What would happen to the derivative? In general, the derivative would also transform, correct. So, I can write a dou bar squared plus what about m? What is m squared? That is an invariant, right, that is a Lorentz invariant. So, that just goes along for a ride, correct. That is the equivalent of the space time interval for energy and momentum, correct, the invariant mass. So, c square remains c square, h bar squared is h bar squared, and again in general it is a psi bar with coordinates x bar equals 0. Okay. So, let us call this frame 1 and frame 2. In frame 1, this is in frame 2, and we just said that we explicitly demanded that psi of x equals psi bar of x bar. So, that is taken care of. Now, we need dou square equals dou bar squared. Now, would that be true? Of course, if you look at the equation as I have written here, for people who know how to contract covariant and contravariant indices, this is manifestly true, correct. But if you are not convinced, go back to how you contract these indices using your favorite metric and convince yourself that this is indeed true. Okay. Written this way, the square of the 4 derivative is a Lorentz invariant. So, that means that is good news, right. That means the Klein-Gordon equation we have derived from the Schrodinger equation using quantum mechanics, and it turns out to be Lorentz invariant. So, that is good news, right. But there is still something we need to understand here. Okay. The way we have written all this is the wave function, correct. The Schrodinger equation does something to the wave function. All we have done is take the relativistic form of the Hamiltonian, square the operator, and written an equation for the wave function again, correct. We have not changed anything else, agreed. So, this is still a Klein-Gordon equation on the wave function. Okay. I keep repeating that word because it has a very important consequence. If this describes the evolution of wave function, then that is bad news, and that is the distinction we are going to make in this lecture and in the next lecture, that we should not interpret this psi as a wave function, but as something else. Okay. Why is this bad news? Why is, if this is a wave function, why is this bad news? Because although Klein-Gordon equation satisfies relativity, it does not satisfy a very fundamental axiom of quantum mechanics. Okay. And that follows from the fact that the Schrodinger equation, necessarily by being first order in time, has ensured that there is unitarity. Okay. Whatever the evolution of the wave function is, there is always going to be unitarity. What is unitarity? Probability is adding up to 1, right. Once you lose that, you are in trouble. Let us see how. Okay. Now, we have 2 derivatives of time, correct. So, let us take the norm of this state, the psi t, right. So, if I take this norm How do I write that? I have basically now summed over all the positions, or basically in this case integrated over all the positions, correct? Agreed? So, this is the norm of the state, and of course, this is exactly what I would write as psi star psi, right. So, what is this? This is the probability, correct. This is the probability density. So, this whole thing is the probability of finding the state, finding the wave function in this particular state, correct. Is not that what Bond rule tells us? So, this is basically this a statement of the Bond rule. Now, this would have been fine if you had had only one time derivative in the equation of motion of the wave function. Why? Because if that were the case, the evolution of the wave function would go like an exponential of I times the Hamiltonian, correct. Remember this from old school quantum mechanics. And if that were the case, whatever the time dependence of the wave function is, right, since I have a psi star times psi, the phases will eat each other, and this whole thing, the entire integral becomes time independent. In other words, if I had had just one time derivative like in the Schrodinger equation, I would have had the probability of finding the wave function, of finding a state in one particular eigenstate, right, to be time independent. Whereas if I had two time derivatives, there is no such guarantee. Like in the Klein-Gordon equation, the probability is time dependent, and that is a bad thing, right, because that does not guarantee that the probability of finding this state in other eigenstates would all conspire such that all these probabilities add up to 1. Agreed? In other words, there is a very good chance that this would violate unitarity. Agreed? So, that is the problem with the Klein-Gordon equation written in this fashion. Okay? This does not mean we should have to throw away the Klein-Gordon equation. It means we have to now interpret this equation in a different way if we were to succeed in putting relativity and quantum mechanics together. Alright. So, what we should not do is to interpret this as a wave function. We have to interpret it in some other way. So, what should we do here? Okay. Notice that in quantum mechanics, there is always something very weird that we, very strange at least, that we do in quantum mechanics. We use position as an operator, correct, but then we never use time as an operator. Agreed? Time is just a label that marks basically the time on the wave function. However, position and momentum are operators, correct, and this is the reason why, although in school we learn about the Heisenberg uncertainty principle in terms of both momentum and position and energy and time, by the time we get to somewhat advanced levels of quantum mechanics, we only see the operator version of Heisenberg's uncertainty principle for momentum and position. We never see the operator version for energy and time, correct? The operator for energy is what? The Hamiltonian. But then we never see some H T operator version of the Heisenberg uncertainty principle, correct? We never use time as an operator. So, in that sense, when we start writing quantum mechanics, we have manifestly violated relativity already. We have already not put position and time on the same footing, agreed? So, that is something we have to rectify right away at the outset, alright. Put differently, we have to find a way to either promote time to an operator or demote position to a label like time. This is to get a sensible relativistic quantum mechanics framework, let us call it that. Do you agree now? At the least we have to do one of these two things, right. So, the first option is something I am not going to talk about in this course. You can go look up Srednicki. It is somewhat horrendously complicated, it is not horrendously complicated, it is definitely more complicated than the second option, okay, and that leads to concepts like world sheet and so on, which is the starting point for string theory, okay. But we are not going to do string theory here, we are going to do the second option which leads to quantum field theory. We are going to explicitly demote position from an operator to a label, alright. Now, when I put it that way, you can ask, okay, it is a label, but label on what? Earlier we saw that time was a label, but it was a label on the wave function, but I just told you that we cannot interpret this as a wave function. So, then what are we talking about? What is this the label on, alright? The answer is, and the only self consistent answer that seems to be working so magnificently is that it is a label on quantum operators, okay. So, what is left in quantum? There is a wave function, the only other thing that is left is quantum operators, right. So, I am going to use both x and t as labels on quantum operators. Now, pause for a second and think about this, okay. We have seen so many operators, we have seen position itself as an operator, momentum operator, spin operator and so on, okay. But these acted on some quantum space, there was some Hilbert space, and then you did some transformations, you had some evolution, etc., right. But now we are claiming that there may be quantum operators that are positions, are functions of the position and time where they are, correct. In other words, we seem to be implying that everywhere in space and everywhere in time, all over space time, there are these weird operators, quantum operators acting on some Hilbert space or some Fock space, correct. That is somewhat of a strange notion, is not it, that a quantum operator actually carries space time label, but that is exactly what we mean by a quantum field. So, when you hear quantum field theory, right, what it means is it is a theory of these quantum fields which are operators that operate at every point in space and time, not on space and time, they are in every point in space and time because they are a field, that is what makes them a field, but they act on some abstract quantum space. In this case it turns out to be Fock space, which is very much like Hilbert space, but with some bells and whistles. Okay. So, that is what we are going to do. This is how we put space and time on equal footing and turn it into something manifestly relativistic, but also use the notions, use all other notions of quantum mechanics. Okay. So, I am going to wrap up this lecture with a slight introduction to natural units. So, what I am going to do is simply rewrite the Klein-Gordon equation here in this form. Okay. So, I am just going to rewrite the Klein-Gordon equation as just del square plus m square. Notice that I have gotten rid of c and h. How did I do that? I did not set c equal to h. Well, in a sense I did, okay. And then I am also going to rewrite the psi, because psi denotes wave function to me. We just saw it is no longer a wave function. Let me just call it a phi. Phi is a good symbol for scalar fields, scalar quantum fields, okay, equal to 0. So, what I have done now is to set c equal to 1 and h bar equal to 1. Okay. So, this might sound crazy to you, but I always have the freedom to do this. Okay. I can always redefine a meter and a second such that c becomes 1, and I can always redefine other quantities like energy and so on such that h bar is also equal to 1. So, we are going to explore some of the other dimensionalities of other physical quantities that come as a consequence of doing this in the next lecture, but I encourage you to work this out yourself. See what happens to the relation between energy and momentum and length and time and so on, okay, if you do this using dimensional analysis. Alright. So, I will leave you here and we will catch up on this in the next class. Alright, thank you.